Alright guys, so this is the slide that we ended up on in the last video, and it was basically 12 points toward green chemistry. Why should I be enthused with green chemistry? What is there for me? What should I take away from it, right? So we talked about all of these 12, and now I just want to talk about a couple of them in a little more detail than maybe what I did in the previous video, and give you a better overview of green chemistry as a whole. The first thing that I want to talk about here is this concept of the least hazardous. This is very important, right? As a company, I do not want my employees to get hurt, right? And as a laboratory worker, you do not want to be exposed to these chemicals that can eat flesh or chemicals that can cause cancer. And you want to minimize your exposure to those. So this is a win-win for everybody. Yes, companies, even big oil companies, people, have your best interest in mind when it concerns these things because they have to. If they do not put you first as far as safety goes, then they can actually be fined thousands and thousands and thousands of dollars, almost to the point that it will put them out of business. So they have to make sure that what they're doing on their location with you working there has to be safe. Now, sometimes companies do slip up, right? And that's a purpose, and that's part of your role as an employee. If you know someone's slipping up, then you need to turn those people in, and there's ways that we can do that. And I'll talk about those ways much later on in the course and maybe in this lecture module, but we'll save that until a little bit later. So you want to select the least hazardous chemicals, keeping in mind the environment and human health, right? We don't want to poison the waters or the air or the soil, and we don't want to poison you either. So when we synthesize compounds, so synthesize is just a fancy word that means make. When we make compounds, we want to minimize, and I'm going to draw an arrow down for minimize, the hazards that are associated with that. And we want to choose compounds that can degrade. Degrade is a very good thing for us. That's supposed to be a check mark. So these are expiration dates basically on chemicals, right? All chemicals have an expiration date. Some of them are within a matter of days once you use them. Some of them could be years and years and years after you open the bottle up. But this degrade idea is very important because that means it will break down, it will decompose, and it will change into something different that's maybe not hazardous anymore. So in a laboratory, if I want to think about green chemistry, I want to design experiments, and I want to keep a few things in mind when I design them. I want to minimize the heat that's associated with the reaction itself. So sometimes you have to mix things together and you have to put them on a hot plate, kind of like boiling water for your spaghetti. If there's a way that I could create spaghetti noodles without boiling water and get them soft, then by all means let's do it, because there's no heat involved and that's better for the environment, and that's maybe green kitchen instead of green chemistry. However, sometimes there's just no way around it. Sometimes you're going to have to use heat, no matter what that purpose is, right? So if you use heat, you could still follow green chemistry, but if you have the concept of minimizing the heat, that's where the green chemistry is coming in. You don't have to use as much, and because of that, you're putting more faith and more trust in your environmental decisions from that point on. You also want to minimize water. Very often in a laboratory, we love to be wasteful with water. Sometimes the water will run all day long in our laboratory, and it just basically comes out of a faucet. It cools the things that we need it to cool, and then it goes down the drain and out the other end. I would hate to see the college's water bill. And industry is the same way. Industry will use tons of water throughout the processes that they will do at their plants. And if I can minimize that water or not use water at all and choose synthesis routes that could not require any of that, then all of a sudden I'm putting the environment first. And that, by definition, is the green chemistry. And then next are pressurized systems. No pressure, okay? The reason that pressure is involved is because it often takes heat to create pressure, and it often takes a lot of energy to basically build pressure up in these systems, whether it's in industry or in our own lab. So if I don't have to worry about building pressure up in a closed vessel, kind of like a pressure cooker, right? Think of a pressure cooker on a stove. The same thing's going to happen in a laboratory. If I can minimize the heat that it needs, if I can minimize the water, if I can minimize pressure if needed, then green chemistry is at the forefront, and that's really what I want to be thinking of. So the way that we kind of do this, or the way that we can kind of help out this, and we've mentioned this before, let me just clear this off, is that we use reagents. Reagents are just a fancy word that means starting ingredients. That's all that they are. Okay, so I can use ingredients in the very beginning that can be recycled. Now, not everything can be recycled or reused, or sometimes we use the word renewable, meaning I can get them back again if I do something to them, right? So I need to be very careful with those reagents that I pick. Those ingredients, those starting amounts, if they do not get used up in the reaction, and let's say I've got some left over, is there a way that I can get the extra back out and reuse it over again? And in a laboratory, sometimes this can happen quite easily. So I want to be conservative when it concerns all of my reagents and my products and my waste, because if I can take an extra 1 or 2 steps and recycle or reclaim those reagents and use them again, then I better, because all of this will save money. And that makes companies, and that makes us in the academic field very happy, because we don't have to be wasteful and spend crap loads of money out just because we're too lazy to take the extra step to reuse it and recycle it. We also want to choose reactions that have very high yields. That was something on the last slide that I want to talk more about. A yield is basically a product, all right? So imagine that you're in the kitchen and you're working with a recipe, and the recipe makes a certain number of cupcakes, all right? So let's say that I could modify or change the recipe up. And when I change or modify the recipe, I still get cupcakes in the very end. But let's say that I can increase the number of cupcakes that I can get from the actual recipe itself. Is there a way that I can do this? So this helps prevent waste, and it helps maximize our product out, so that way we don't have to be wasteful and spend tons of money that we don't have to spend in order to get the same amount of product. Now, in a recipe, I guess the best way to think about this is, let's say that you're making the cupcake batter, and let's say that you give someone the chore of putting the cupcake batter in the cupcake tins, right? And they put them into the oven. Well, let's say that they put the cupcake tin in the oven, it's completely full, they still have batter left over in the bowl, and instead of making a second batch or putting them into a second pan, they just go over to the sink and they just dump the good cupcake batter out into the sink and washes it down the drain. Those are the things that we need to think about. We don't want to be those types of people, right? We want to make common sense decisions. We want to make sure that we increase our product yield. And if we need to change something up in the reaction or in the method or in the steps, then we're going to do that to make sure that we maximize the product. So in that scenario, if we only had one tin, common sense would say, take the cupcake pan out, dump the cupcakes out onto a pan to let them cool, and then take the same cupcake pan, put the remaining batter in the cupcake pan, and put it back in the oven, right? I mean, that's what anyone would do if they had common sense, right? They wouldn't take the extra batter and say, oh, well, I ran out of pans. I guess I'll dump this down the sink. I don't need that anymore. Don't be one of those people in a lab, and I think that you'll be good, all right? And then finally, we want to design procedures that have recyclable waste. We want to take a look at the waste that gets generated from the reaction. And we know that the waste is waste. We don't need it. So if we do not need it, is there a way that we can reuse this in some form or in some fashion? Can we take the waste and maybe sell it to another company? Because maybe they will use that waste product in their production environment. And if so, then I get some money out of it, right? Or can we reuse the waste? Meaning if we get a product that we don't necessarily need, can we at least save that product because maybe somewhere else in my company they're using that product for another purpose? And if so, then all of a sudden I've got green chemistry at the forefront. And that's really what I want to do, all right? Okay, so if I change over to the PowerPoint slide again, I'm sure that many of you have seen some types of drains or some types of runoffs that look like this. They're just huge, big industrial pipes with a lot of nasty, brown, sludgy water or waste that's coming from it. What I want you to understand is that this dumping that people talk about, it's very commonly done. All right. If you go up through the Cape Fear River and you go all the way up to the northern part of the state, you're going to see tons of companies dumping stuff into the Cape Fear River because it is legal to do, right? As long as their waste is getting recorded and tested, and as long as they can prove that the waste is not going to be an environmental danger to anything, whether it's to the fish or to the water or to the soil or to the people around it, then they can legally dump things into water streams like this and carry it away. It's got to go somewhere, right? Just like your kitchen at home. You've got waste that could be from your dishes at your house. And then when you go and you wash your dishes, where's that extra food going, right? Are you dumping it down your garbage disposal and sending it through your pipes? Are you dumping it into your trash can so that way the trash people can take it off and take it to a landfill? You're generating waste, people. And you're no different than a company. A company has to generate waste as well. And that waste has to go somewhere, just like it has to go somewhere at home, whether it's in your disposal or whether it's in your trash can. So the 19th and 20th centuries, those were the 18 and 1900s, little was known about this waste, about chemicals, the environmental dangers that can be associated with them. And because of that, this was just commonly dump, 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 no questions asked. However, 1963, we get what we call the Clean Air Act. And then in 1974, we get the Clean Water Act. And then in 1976, we get the Toxic Substance Control Act. And then in 1976, we get the Resource Conservation and Recovery Act. So the mid-1900s and on is when we began to really focus on waste. What can reagents and chemicals do to the environment and to the people that live around those companies? And we wanted to make sure that we minimize all of the risk that are associated with those reagents. So finally, the American Chemical Society established the Green Chemistry Institute. It's basically an institute promoted by the ACS, American Chemical Society, that kind of trains us to be more green, more environmental friendly. And what are we doing to make sure that we are green? And what can we implement or change in the future to make sure that we stay green in our academic labs or into our industrial labs? So we are paying attention to it. There are things, however, that can happen. And as a part of living in North Carolina for the past so many number of years, if you've lived here in 2017, 2018, you will constantly read stories about this GenX. Okay. Now, what I want to say about GenX, Chemours is the company that produced GenX. GenX was a compound that they were using in their Teflon production. They had used a previous compound, but the previous compound was claimed to be environmentally hazardous. And they made the decision to change this compound into a more environmental friendly one. And that was called GenX. All right, well, GenX began to be used in the manufacturing process of their Teflon. So if you bought Teflon, whether it's at home with your skillets or whether it's at home with your utensils, whether it's Teflon tubing that is found in your refrigerators that carries the water to your water source through your water filter and out the dispenser, all of that Teflon type of product was getting basically produced by using GenX. And GenX is also somewhat of a waste product. That means that once they use GenX in the production, they don't really need it anymore, and out it comes, and they discharge it into the Cape Fear River. This had been going on for years, 10, 20 years at least. And finally in 2017, 2018, we had a professor from NC State University that was working on a grant. And the grant was basically monitoring organic contamination in a water source. For a couple of years, this professor began looking at these results and knew the presence of GenX, but really probably didn't know what it was at the time, but he at least found the compound. And then after a couple of years, when his research grant came up for renewal, he goes to the media and he releases the studies and the findings about GenX. And the media picks it up. And the media goes rampant with it. And it scares everyone up with GenX. Well, at the same time, this professor applied for a new grant. He probably received the new grant and the grant money that came along with it to continue to study the presence of GenX in the Cape Fear River. At the same time, though, people were scared that this part per trillion compound, super low levels, only 2 labs within the entire state had the capability and the technology to test for GenX. Anyway, the GenX at super low concentration levels basically was thought to cause cancer in people. And they began to look at studies of cancer, and they saw that especially in men, testicular cancer was higher in the Wilmington, New Hanover County area than anywhere else in the state. Whether those two are related or not, it's who knows at this point. But it just so happens that if one goes up, the other goes up, and whether or not they're related to each other, that needs to be proven. But what I want to say is that Chemours was legally dumping GenX into the river. They were not breaking any law. As bad as the media wants you to believe that, they were not breaking any law. GenX was not a regulated chemical. GenX was getting dumped into the water legally because the Environmental Protection Agency, known as the EPA, did not care about it. Then once these studies came out and once the public discourse came out, the EPA looked at this molecule and says, okay, we're going to establish a limit on it to make people feel better. And they gave us a limit on GenX now. Up until that point, though, Chemours was doing everything legally. They were not breaking any laws at all. And if you want to go through and take a look at this link, I'll have this link accessible in Blackboard, and you can read the article about Chemours, and you can read the article about GenX as well, and the EPA's role in managing GenX from that point on. So all chemical industries discharge. There's nothing that you can do about it. There's no way around it. You're going to get discharge from a company no matter what type of company that it is. Whether it's a chemical company or another type of manufacturer that is up and down the rivers or the lakes or the streams, you're going to get waste, people. That's just the fact of life. How to handle the waste is the goal. What can we do with this waste to make it better? What can we do with the waste to make it more green or more environmental friendly? What can we do with the waste to minimize the health risk that are associated to the employees or to the students? Now, the goal here, you don't have to worry. The only thing that you have to do is follow directions. Many entry-level employees, many students are not required to think about these things, right? They're just too inexperienced to do that. So as long as you follow directions, as long as you do what they tell you to do in a lab, then you're good. you are implementing green chemistry because that has already been built into the system. People that have been there for a while, or people higher up on the ladder, will look at all of these other things that they have to worry about and realize and think of how to minimize the waste and the hazards that are associated with the waste. So one last slide. Use safer solvents, less flammable, less toxic. Reduce volumes and amounts. Microscale versus macroscale, right? So sometimes in a lab we can do very small portions and not really huge big portions. Think of it as cooking dinner for your family or cooking dinner for a party of 100 at a wedding, okay? That's microscale and macroscale. Minimize hazardous byproducts. Nitric is an excellent oxidizer, but it produces noxious gases. Chromium-6 is carcinogenic. It causes cancer. But if I can choose hydrogen peroxide, it does the same thing. And it gives me water as a byproduct. That's a perfect example of substituting a reagent and make it more green. Use bleach instead of chromium, which is carcinogenic, or nitric, which is very noxious. Use less toxic reagents and minimize the waste. Recycle them, use them for another procedure, sell them for another company. All of that is green related. So thinking green, right? That's kind of our concept. That's part of what we want to do in a laboratory, and that's part of what we do in our program. So that's where this module is going to stop. Hopefully you get a better idea of what green chemistry is now and how to handle that into a laboratory. And then stay tuned because there's more videos that are associated with this chapter. So come back, we'll sit down with each other again, and we'll talk about the next topic.